Hello everyone, welcome to lecture series on digital image processing. Myself Placin Dias, Assistant Professor, ENC Department, KLS VDIT, Haryana. Today we are covering a content related to image smoothing. Learning outcome of this lecture is a student will have a better understanding of image smoothing using low pass filter. We have covered in the previous class the information related to filtering in frequency domain. So let us revise some of the things related to filtering in the frequency domain. The picture represents the damaged IC with its Fourier spectrum. The basic mathematical equation which is represented in frequency domain related to filtering is given by g of x comma y equal to real part of transform inverse, that is inverse discrete Fourier transform of h of u comma v into f of u comma v. Here f of u comma v is Fourier image of input image and h of u comma v is Fourier image of transfer function, that is filter transfer function. We have to remember that filtering in the frequency domain consists of modifying the Fourier transform of image, then computing the inverse transform to obtain the special domain representation of the process result, isn't it? So the same has been represented by a block. As I said, the filtering in the frequency domain is nothing but modifying the Fourier transform of image. So input image f of x comma y is pre-processed and fed to the block of Fourier transform, wherein we obtain the Fourier image of input image, which is represented by f of u comma v. The same is passed to filter transfer function, which is represented by h of u comma v. So the output of filter function is Fourier image, that is f of u comma v multiplied with a transfer function image h of u comma v. The result is passed to inverse Fourier transform block, wherein we get inverse discrete Fourier transform of h of u comma v into f of u comma v. So the resultant value will be a special domain representation of an output image, which is an enhanced image represented by g of x comma v. In the previous class, we have covered the content related to low pass and high pass filters. The figure represents the how the IC will look in after low pass filtering and after high pass filtering. As we can see from the picture, the original IC which was damaged and we had seen its Fourier spectrum, isn't it? So once it is a low pass filter, the blurriness has been increased in the original figure. When we pass it through high pass filter, we are able to see a dark image, and the one more characteristic what we are able to observe here is the edges of the damaged IC has been observed very clearly. So low pass filtering normally contributes for smoothing operation, and high pass filter contributes for sharpening aspects of an image. The one more filter that we have studied was Gaussian filter. isn't it? So the transfer function of Gaussian filter is represented by h of u in a frequency domain. So Gaussian filter function is given by h of u equal to a into e raised to minus u square divided by 2 sigma square. Here, sigma is the standard deviation of the Gaussian curve, and the corresponding filter equation in the special domain is given by h of x equal to root 2 pi sigma into a into e raised to minus 2 pi square e square 2 pi square into x square into sigma square. So one of the useful property of the Gaussian function is both its and its Fourier transform are real valued. There are no complex values associated with them. In addition, values are always positive. So convolution of an image with Gaussian function, there will be never any negative output values to deal with. So there is an also important relationship between widths of Gaussian function and its Fourier transform. If the width of the Gaussian function is smaller, the width of the Fourier transform gets larger. This is controlled by the variance parameter sigma square in the equation. So that is a relation between the Gaussian function and its Fourier transform. And we are able to see the clear representation of Gaussian filter in low pass filtering as well as high pass filtering. So as we had seen, there is an important relation between widths of the Gaussian function and its Fourier transform. So we'll continue with the today's class, wherein we are able to see the image smoothing aspects of the digital image processing in frequency domain area. Okay, so let us understand first what is smoothing. Okay, smoothing or blurring is achieved in frequency domain by high frequency attenuation, wherein we have to attenuate the high frequency values. So that means we have to use a operation which is called a low pass filtering, isn't it? So let us understand the basic mathematical equation used for filtering in the frequency domain. So basic model for filtering in the frequency domain is given by g of u comma v equal to h of u comma v into f of u comma v, isn't it? Smoothing is fundamentally a low pass operation in the frequency domain, isn't it? So input image or Fourier transform of image is f of u comma v, and its filter transform function is h of u comma v. So there are three different types of low pass filters that can be used for image smoothing. The first being ideal low pass filter, second is Butterworth low pass filter, third is Gaussian low pass filter. So let's see the first one, that is ideal low pass filter. The simplest of low pass filter is ideal low pass filter. Okay, so which cuts off all high frequency components of the Fourier transform that are at distance greater than some specified distance d naught from the origin of the transform. So here d naught is considered to be a positive constant and we call it as cutoff frequency. So all the content which are above the specified distance d naught are cut off, or we call it as high frequency components are cut off by the filter. So it will pass only the low pass filtering content. So let's analyze transfer function of an ideal low pass filter. So basically filter transfer function is represented by h of u comma v, isn't it? So we have two values represented, 1 and 0. So if d of u comma v is less than equal to d naught, we have h of u comma v as 1. Okay, and if d of u comma v is greater than d naught, we have h of u comma v as 0. So here d of u comma v is the distance from point u comma v to the center of their frequency rectangle. So as we had seen with the distance measure aspects, in distance measures we had studied three different distance measures. One is Euclidean distance, second is chessboard distance, third is city block distance, isn't it? So let us recall the Euclidean distance formula, because that will reflect here in d of u comma v calculation. So the formula is represented by u minus p divided by 2 whole square plus y minus, v minus q by 2 whole square raised to 1 by 2, isn't it? So it is resembling Euclidean's distance evaluation. In the next figure, we are able to see the perspective plot of an ideal low-pass filter transfer function. The first figure represent the actual low-pass filter transfer function plot. The second, that is middle one, is representing filter displayed as an image, wherein we are able to see it as just a kind of circle representation. In a third figure representation, we are able to see the filter radial cross section, isn't it? So where h of u comma v is represented on y-axis and d of u comma v is represented on x-axis with d naught as a positive constant value. So we are able to see up to d naught from the origin, and the values are high, that is value represented with 1, and the remaining values are 0 on the filter radii cross section representation. So in the figure, the image size here for a given figure is almost 500 to 500 pixel, and its Fourier spectrum is represented. So what we are able to see is superimposed circles. Okay, superimposed circles with almost different radii. Okay, so the given picture represents superimposed circles with the radii of almost 5, 15, 30 and 230. Okay, so, such superimposed circles with the different radii, they enclose some part of the image power. Okay, for a given picture, the percentage of the power which was considered is almost 92, 94, 96, 98 and 99.5%. So what it means to us? Okay, so what we are able to see is, once we have that 98 or 92 percentage of image power, there has been some power removed from these filters, isn't it? So might be the value will go depending on how we have taken the percentage. So if you are taking 92% means almost power removed is now 8, isn't it? So in the next picture, we are able to see the clear difference. If the ideal filter is having cutoff frequency set at radii 5, 15, 30, 80 and 230, and power removed by them is 8, 5, 4, 3, 3.6, 2 and 5%, isn't it? So we can see the difference in original image and their successive image with the power removed from the given filter, that is ideal low pass filter. So second picture is almost a blur, and the last picture is the clear representation of the original image, isn't it? So we can see as the power removed by these filters are varying, the effect on the original image is changing. So let's see one more example wherein frequency domain uh, ideal low pass filter of radius phi is considered, okay, and its corresponding special filter value is represented. And in second, we are able to see some 5 impulses in the spatial domain, simulating the values of 5 pixels, and convolution of those second, that is corresponding spatial filter value, and the third, that is 5 impulses in the spatial domain. So as we know, the basic equation of convolution is f of x comma y into h of x comma y, which will be transformed into capital F of u comma v into h of u comma v, isn't it? So the first figure represent uh, one single pixel and its spatial representation, and in second figure we are able to see 5 impulses in spatial domain. So the last picture shows the convolution of those 5 impulses, and the spatial domain multiplication, that is convolution multiplication with the given pixels. So we are able to see the convolution of those two results in spatial domain. Let's understand what is a Butterworth low pass filter. So here the equation is represented by h of u comma v equal to 1 divided by 1 plus d of u comma v divided by d naught raised to 2 into n, isn't it? Here Butterworth low pass filters are represented by order n. The picture basically represents perspective plot of Butterworth low pass filter transfer function. And the middle figure represents filter radial cross section of order 1 order. The last figure represent for a different order of n values, basically starting from 1 to 4, how the picture graph looks, isn't it? So because as the order is increasing, as we are able to see n equal to 1, we are getting a smooth curve, isn't it, starting from almost 1.0 to the value of representation on x-axis as d of u comma v. There is a smooth fall, wherein whenever the order is increased, that is n equal to 4, so we are able to see the sharpness of the curve for the same value, or reaching almost near to d naught, isn't it? That is a difference for the Butterworth low pass filter. So let us see the third low pass filter, which is used for image smoothing, that is Gaussian low pass filter. So transfer function has the form h of u comma v equal to e raised to minus d square of u comma v divided by 2 d naught square. Here sigma is the measure of the spread about the center, and d naught is a positive constant. Okay, so if you see the original equation and the new form of transfer function of Gaussian low pass filter, here sigma is equated to d naught, isn't it? So D naught is considered to be cutoff frequency, and whenever we have D of u comma v which is equal to D naught, Gaussian low pass filter transfer function is almost down to 0.607 of its maximum value of 1. Okay. So it will have a value 0.607 of its maximum value of 1. So we can see the clear difference in perspective plot of GLPF transfer function, then filter displayed as an image, and the last uh, representation shows graphical or the characteristics of Gaussian low pass filter when the order value or various values of D naught, okay, filter a radial cross section for various values of D naught we are able to see. So as we can see now, here in the graph the values for D naught was considered as 10, 20, 40 and 100, isn't it? So when D naught is increased to 100, the curve is taking a smooth representation. Sharpness is increased for a lower value of D naught, that is D naught equal to 10. We have the sharp representation of the content. So let's see now one of the picture wherein I think we can identify how the things will change when we vary the value of D naught, wherein D naught is considered to be a positive constant value either in Gaussian low pass filter or Butterworth low pass filter. So here the image taken with the original image, which is taken with the pixel value as 1028 into 732 pixels, okay, and the middle figure represents filtering with the Gaussian low pass filter with the D naught equal to 100, and the last figure, that is third figure representation, is result of filtering with Gaussian low pass filter with D naught equal to 80. Okay, so what we are able to see the difference with the D naught equal to 100 set and D naught equal to 80 set for the given image. So what we are able to see is reduction in skin fine lines. In the magnified sections we are able to see the difference related to original image. So as we had seen from the previous graphical representation, that whenever D naught is less or D naught is less, sharpness of the image is clear, isn't it? Or we are able to see the clear fine skin fine lines of the image when D naught is lowering, that is D naught equal to 80. So let us try to summarize the today's lecture class. That is, what is the effect of low pass filtering? Okay, or what is low pass filtering? Or low pass filtering is nothing but a smoothing operation, which is employed to remove high spatial frequency noise from a digital image. Second thing that we have understood is the low pass filters usually employ a moving window, isn't it? Moving window operator, which affects one pixel of the image at a time, changing its value by some function of local region or window of pixels. So let us understand some of the applications of smoothing filters. So smoothing filters are used for noise reduction and blurring operations. Okay. So image smoothing is a key technique of image enhancement. Smoothing is performed by spatial and frequency filters. I hope today's lecture content related to image smoothing was most understandable to you. Uh, Thank you very much.